Okay, let's say that I need to solve the following very simple ODE. Second derivative of y, unknown function y, with respect to x, is equal to some function f at point x, y, and first derivative of y with respect to x. Okay, let's say that I need to solve this equation in the region where x ranges from some a to b. I need to solve this equation in this region, okay? So, so far, we learned how to solve this equation when we have some initial conditions, right? When we have some initial conditions. So, which means that y, we need the value of y, function y at point A. Let's call it ya. And also, we also need the derivative of the function y at the same point. Let's call it ya prime. So, this kind of problem called initial value problem, okay? Just to remind you, in order to solve it, we introduce a new variable, let's call it z, which will be equal to dy dx, first derivative of y, such that second derivative of y will be first derivative of z, dz dx. Instead of second derivative of y with respect to x, we have the first derivative of z with respect to x, and that should be equal to the right-hand side of this equation, f, x, y, and z. Okay? So then, solving this system of second-order ODE boils down or translates to solving system of two first-order ODEs. Similarly, if you had system of, let's say, third-order ODE, we would be able, in a similar way, to transform in a system of three first-order ODEs. Generally, if you have a system of nth-order ODE, if you have a nth-order ODE, we can transform it to a system of first-order ODEs of n equations, okay? So we have second order, we get two ODEs of first order, system of two ODEs of first order. So, and then these conditions will translate to y of a is equal to ya, and z of a will be equal to some ya prime. This system we know how to solve. We learn how to solve it. We can apply Euler's method, Heinz method, midpoint method, fourth order Runge-Kutta method, whatever we want. We know how to solve this. Okay. So today we'll consider different types of a different type of problem called a boundary value problem. This problem which we just described is called initial value problem. Initial value problem. Why? Because we have the values of y at initial point, at point A. We have to solve this equation from A to B. We know y and its derivatives at point A. So information is given at the beginning. In the boundary value problem, part of the information is given at one boundary and some part of the information is given at other boundary. For example, at the boundary value problem for this ODE may be the following. We may know the value of y at point A. Let's again call it ya. And we may know the value of y at point B now, instead of its derivative. This is one option. That's not the only option. For example, we may be given derivative of y at point A and the value of y at point B. Or we may be given derivative of both functions at points A and B at the boundaries. Okay? Or finally, we may be given the value of y at point A and the derivative of y at point B. Different combinations. But most importantly, one condition is given at one boundary and another condition is given at another boundary. If you had system of three equations, we would need three conditions. In that case, two conditions can be given in one boundary, on one boundary. One condition can be given on another boundary. Okay? So part of the conditions are on one boundary. The remaining conditions are on the other boundary. That's why it is called boundary value problem. Conditions are given at the boundaries. All right. So how shall we solve this? How shall we solve boundary value problem? Okay, there are many different types of problems for solving boundary value problems. We will consider two types of those methods today, some of the most common and popular methods. First one is called shooting method. And the second method which we will consider is called finite-difference method. Finite-difference method. All right, let's start discussing this shooting method. All right, the shooting method. I am trying to solve a boundary value problem for the same equation. So I have second order ODE. Second derivative of y with respect to x is equal to some function f x y dy dx. I need to solve it in the region from some a to some b. And let's say that these are my boundary conditions. I know y, function y, at point A and at point B. Okay, I need to solve this with the shooting method. All right, so how shall I approach this guy? So, I know y of A. It is ya. I'm just repeating what I wrote there. All right, so in order to apply the methods which we discussed before, the methods for initial value problem, the only thing which is missing here now is the value of the derivative of that function y at point A. So this is missing. Okay, this is missing. But what I'm going to do now, and that's the main idea of the shooting method, I'm going to guess. I'm going to guess this value and solve it. Solve this equation. And try to find, from using this u, I will try to find the value of value of y at point B using this guess. And this is how I will denote this. Okay, so I'm going to guess the value of the derivative of y at point A. Using that, I will solve it using the methods which we discussed last lecture, for example, Euler's method, and I will find the corresponding value of y of b. Okay, I will find the corresponding value of y of b. And then I compare whether what I got as a result is the same as what is given. If they are the same, which means that I guessed it right and I got the correct result. If they are not the same, it means that I didn't guess it right, so I'll keep trying different values of y. That's the main idea of the shooting method. All right? So how I can implement it in the most efficient way. All right, so let's first draw exact solution. Let's say this is my exact solution. This is my x-axis, this is my y-axis, and let's say this is how the function y behaves in this region. It ranges from A to B. All right? So, as I said, I guessed its value initially, and using that guess, let's say this was my solution. I arrived at this point. So this would be yb using y, whereas this guy is yb. There is some discrepancy. Okay? So what I can do, I can try to minimize the following function. yb calculated using some guess u minus yb, the actual value, should become 0, right? Ideally, these two should become 0. Okay? And this is a root finding problem now. This is a root finding problem. In other words, I have to find, in this equation, I have to find such u that gives 0, that makes this guy 0. That is a root finding problem. So we can use, let's say, some root finding iterative schemes like fixed point iteration or secant method, different methods which is suitable for this particular differential equation. And using those different methods, we can try to find this u which solves this equation, which gives a 0 here. Of course, at each iteration, we start from one guess, another guess. At each of those iterations, at each of those refinements of my guesses, of course, I have to solve initial value problem, right? For these sets of initial conditions, for each u, at each iteration, I have to solve initial value problem here and try to see whether I'm approaching or not. And I stop root finding iterations when I get sufficiently close to this value of yb. When this guy becomes sufficiently close to this guy, in other words, which means that when it is 0. Using the conditions for stopping iterations which we discussed for root finding, which was namely when the values of u between subsequent iterations becomes sufficiently small. Okay, so this is the idea of the shooting method. Okay, so that's how the shooting method works. Next thing we will discuss is the finite difference method. for the solution of a boundary value problem. In order to demonstrate the finite difference method, I'm going to consider a very specific ODE that describes some physics problem. Second derivative of t with respect to x plus some constant h prime, constant ta minus t is equal to 0. My unknown function is t, so I have to find t of x, and I'm given boundary conditions. T at point 0 is equal to some t0, and t at point L is equal to t some TL. So I need to find t between 0 and L, okay, between where x ranges from 0 to L. Okay, so which physics problem this equation describes? It describes the following problem. I have a thin rod stuck between two walls, and these two walls are kept at two different temperatures. This part is given at temperature T0, and this part is fixed at temperature TL. Okay, temperature at this here and here are fixed for these specific boundary conditions. Okay, I have boundary conditions where temperature is fixed. By the way, this kind of boundary conditions, where the value of the unknown functions are given at the boundaries, are given Dirichlet boundary conditions. Dirichlet boundary conditions. Okay, so these are the boundary conditions which I am given. All right. So TA is the temperature of the surrounding air. Here and here I have a surrounding air, and there is a heat transfer between this rod and this air. Okay, and this coefficient H prime characterizes that heat transfer rate. So what T of x is then, this T of x is then, is the value of temperature as a function of variable x. I introduce my x-axis, so my x equal to 0 corresponds to the left border, and the x equal to L corresponds to the right order. So T of x is a function that gives me temperature at every point. Okay, so this is the setup of the problem. Now, finite difference method. What is the idea behind the finite difference method? The idea behind finite difference method, instead of getting t at every possible x, instead I look for t at some specific discrete values of x. From continuous x, I go to discrete x. I call it xi multiplied by some delta x. In other words, I divide this region from here to here into some specific equidistant points with a size of delta x. Okay, so let's say that I divide it into, I don't know, 6 points. This will be my point 0. This will be my first point, second point, third point, fourth point, and fifth point. To be specific, let's say I divide it into 5 points. Okay, 5 different points. So it's my 0, 4, 1, 2, 3, 4, and 0.5 here. So last point, this point is 0.5. So that point with index 0 and 5 correspond to the left and right boundaries. All right. So instead of x, now I have this discrete x, where I ranges, in this specific case, from 0 to 5. It does not need to be 5. It can be 10, 20. That depends on how much precision I want. But for the moment, let's just say that I have only 5 points. All right. So that's the main idea. Instead of continuous x, I have some discrete values of x. Some discrete values of x. Okay. Now, at those values of x, I need to find the temperature. So I need to find temperature at those values of x. Let's say xi. Which, in other words, temperature at some point xi, I call it Ti. So I need now to find these Ti's. All right, now, so I came up with my set of points, my set of discrete points. The next thing now, to translate this equation, to see how this equation translates to this finite difference language. Okay, what we need to do that? Here it's very easy. I have temperature here. This term is very easily discretized. I just write this equation at these different points. So this one will be just Ti at point xi. What about this guy? Second derivative of t. So far, we learned only how to calculate the first derivative discretely, right? For example, if you apply centered formula to derive first order of derivative of t with respect to x at point I will be, according to the formula which we studied at the beginning of this class, will be t at x I plus 1 minus t at x I minus 1 divided by 2 delta x. In other words, t I plus 1 minus t I minus 1 divided by 2 delta x. Okay, we can derive similar expression for the second derivative. There are different ways we can derive it. We are not going to show how exactly to derive it, but we can derive an equation for the second derivative of t. And an equivalent, so the version of this formula for the second derivative, this is, by the way, the center formula for the derivative, right, for the first derivative. The center formula for the second derivative has the following form. Second derivative of t with respect to x at point I will be t I plus 1 minus 2t I plus t I minus 1 divided by delta x squared. This is the version of this formula for the second derivative. All right, now I have to put this guy into this expression. What do I get is the following. T I plus 1 minus 2 t I minus t I minus 1 divided by delta x squared plus h prime t a minus t I is equal to 0. All right, so I wrote this equation for my finite difference grid, for the grid of my discrete points. All right, now I still have to find these ti's now. What shall I do? I'm going to rewrite this equation in a slightly different way. Minus ti minus 1 plus 2 plus h prime delta x squared ti minus ti plus 1 is equal to h prime delta x squared ta. All right. To make the notation shorter, I'm going to call these guys gamma, and I'm going to call these guys psi. Okay. So let me rewrite this equation now. All right. So I'm going to rewrite this equation using these new variables, new quantities which I introduced. So it will become minus t I minus 1 plus phi ti, not phi, gamma ti, minus ti plus 1 is equal to some psi. So here is my equation now. Here is my equation. Here's my equation. Here is my finite difference equation. All right. So I can write this equation for every I. For I ranging, for every interior point. I need to find this temperature at these interior points, right? For I ranging, so I need to find ti's for I ranging from 1 to 4. Because t0 and t5 are boundary conditions. This guy, t0 and t5, they are given to me. They are given by boundary conditions, right? These guys I know. This is equal to TL. As we said at the beginning, t0 is t0. We called it t0 from the very beginning. Okay, these guys I know. What I don't know is these guys. Temperature here, 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 here. In other words, in the interior points. All right, how can I find it? The answer is this equation. Let me write this equation for I equal to 1. So it's minus t0 plus gamma t1 minus t2 is equal to psi. All right, now let me write the same thing for I equal to 2. Minus t1 plus gamma t2 minus t3 is equal to psi. Let me equal to I equal to 3. Minus t2 plus gamma t3 minus t4 is equal to psi again. Finally, I'm going to write this to I equal to 4 minus t3 plus gamma t4 minus t5 is equal to psi. I get a system of equation. So if I write this equation, at every interior point, I get a system of linear algebraic equations for unknowns. What are my unknowns? My unknowns are t1, t2, t3, and t4. Okay, so these are 4 equations for 4 unknowns. This guy and this guy, I know. They are given by boundary conditions. The rest of the terms, I don't know. So the solution of this equation, linear algebraic equations, which we know how to solve, right? We studied different methods for solving linear algebraic equations. The solution of this equation will give me t at every point. Will give me at every point. By the way, this represents a tri-diagonal system. And for tri-diagonal systems, we learned an efficient algorithm called Thomas algorithm, right? So I can apply the Thomas algorithm and I find t1, t2, t3, t4. Okay? So in other words, initially we had a differential equation. Initially we had this differential equation. Second derivative of t with respect to x minus h plus h prime ta minus t equal to 0. So the solution of this differential equation, I formulated it as a solution of the following, of this finite difference equation. This finite difference equation, I apply this finite difference equation at every interior point, and I get a system of algebraic equations. From differential equations, I arrived at system of linear algebraic equation. So the solution of this linear algebraic equation gives me t at these discrete points. Okay? So that's the idea behind finite difference method. Okay, very good. So this is a one particular case of finite difference method. To make it more accurate, for example, I have, in this particular case, I have t at the specific 4 interior points. If I want to have at more points, in other words, I want to have densely populated points so that I have temperature at more values of x. In other words, if I want to have a more accurate result, what I can do, I can take smaller delta x, which means I can take larger number of points. In which case, I'll get a system which is larger too. The order of the system is equal to the number of interior points which I have here. In that case, I will get a more accurate result. You can also see why we get more accurate result by the fact that this equation has some truncation error, right? Truncation error. The truncation error will be proportional to this delta x squared. So if we decrease delta x, the truncation error of this equation, and as a result, truncation error of this differential equation will also decrease up to a certain point, until you get dominated by round of errors, of course. All right. Now, what happens if I am given not this boundary condition? In other words, if I don't have directly a boundary condition, which means I'm given the values of t here and here. Instead, let's say I'm given the derivative of t. Let's say, to be specific, I'm given dt dx at point 0. Here I'm given now derivative dt dx at point 0. Let's call it t0 prime. How we solve this case? How do we solve case? Let's consider that next, okay? Let me just mention, before we describe the method, that when derivative boundary conditions are given, that situation is called Newman boundary condition. The name for that kind of boundary condition sometimes is Newman boundary condition. People call it Newman boundary conditions when we are given derivatives of the unknown function at the boundaries. Okay? So let's describe how we can solve this case when we have derivative of t at one boundary using this finite difference method. All right, so again, I have to solve this equation. Second derivative of t with respect to x plus h prime ta minus t equal to 0. I have the following boundary conditions. dt dx at point 0, I call it t0 prime. And I have t at point L, I call it TL. How can I solve this condition? All right, so again, I need to discretize this equation at discrete, and I get this equation. That's fine. So the next thing I need to do, I have to discretize this equation. In other words, I have to get a finite difference version of this boundary condition. Okay, again, I have a first order derivative, and in order to express first order derivative, I will just use the centered formula. Okay, I will use the centered formula. For that, I'm going to introduce an imaginary point for the moment on this side. Imaginary point. Let's say that I have an imaginary point on this side. Let me call it -1. I have a point here. And I introduce t-1 here. Okay, I have t1, t0, and t-1 here. And I am given boundary condition, this boundary condition, dt dx at point 0, which is right here, is equal to some t0 prime. Okay, so t0 prime dt dx at point 0 is equal to, if I apply the centered formula for first order derivative, will be t1 minus t minus 1 divided by 2 delta x. From this I can find t minus 1. T minus 1 will be t1 plus, no, minus 2 delta x dt dx at point 0. All right? So using centered formula for the first derivative and this boundary condition, I estimated what should be the value of temperature at my imaginary point. All right? Now I'm going to use that information to create my system of linear algebraic equation. Now I write this guy at point I equal to 0. What I get is minus t minus 1 plus gamma t0 minus t1 is equal to psi. Okay, now I apply it to I equal to 1 minus t0 plus gamma t1 minus t2 is equal to psi, and so on. I keep applying this formula at all the interior, in the rest of the interior points, and finally for I equal to 4, I get minus t3 plus gamma t4 minus t5 is equal to 0. Now what I get is a system of 5 equations. Now I have a system of 5 equations. What I got here represents a system of 5 equations for 5 unknowns: t0, t1, t2, t3, and t4. Okay? Instead of 4 in the previous case, when we had a directly boundary condition, now I have 5 unknowns. Why it is 5? It is 5 because I don't know t0 anymore. I don't know t0. I have to find t0 also. I don't know the temperature there. I know the derivative of the temperature there, which is given by this guy, but I don't know the temperature. So I have to find that too. And the solution of this linear algebraic equation gives me exactly that. Okay? So this is how we can implement Newman boundary condition, derivative boundary condition. Okay, that's all I wanted to say for today.